Hi, so I'm going to talk about the decentralized organic and nitrogen removal, again using a microbial fuel cell for treating domestic waste in rural Ghana. So why do we want to use a microbial fuel cell to do this kind of work in the developing world? Well, poor sanitation is a big problem. We have over 1 million people in the developing world who lack safe sanitation and adequate sanitation. So if we can treat waste using waste that goes into a latrine system. Latrine is a very common way for people to use to get rid of their bodily waste. And so if we can use that MFC to treat that waste, we can provide clean water back into the environment and also produce an incentive for the developing world, which would be the electricity that we can produce from using this MFC. And in the area that we put in our system, Agona Niacrom, there were already 3 cases of cholera. So by improving sanitation, we're trying to diminish disease as well. So why Ghana? Well, we had our pre-established community connections in that area. So in order to have a successful project in the developing world, we need to have strong community relations so that the community feels invested in having this new technology so that they can use it, because sometimes they're unfamiliar with such systems and they don't want to use it. So we were grateful that we had a good community that was really invested in this system. And also we decided to put the actual MFC and latrine in a residential high school that had poor on-site latrines, but had latrines nonetheless, and had some electricity in the school, so that if the system didn't work, because it's still very experimental, they weren't going to be solely dependent on this system. So this is our schematic for the microbial fuel cell in Ghana. So we have the latrine, and it goes, solid waste is composted, and it's filtered out in this composting chamber. And then the liquid waste that contains soluble COD will go into the anode chamber. And both the anode and the cathode have graphite granules as the electrodes. And so the biofilms that develop around these electrodes oxidize the COD in the anode. And concurrently, we also have a nitrification system where urine from a urinal diversion system goes into this to provide the ammonia that's needed for the nitrification process. And then effluents from both the anode and the nitrification chamber go into the cathode, where the nitrates act as the electron acceptors here. We have denitrification, and that means that we have a treated effluent that is low in organics and low in nitrates. So in the laboratory, we set up a pilot system that was to simulate exactly what was going to happen in Ghana, and we divided it into 2 phases. So in phase 1, we bypassed the nitrification chamber and only focused on the anode and the cathode chambers. So we fed the anode acetate only, and the cathode was only nitrate. And these were very large systems. It was 28 liters of graphite granules in both systems and 20 liters of liquid. So this is a picture of both the anode and cathode in the laboratory, and they're both anaerobic, so they're sealed off. And this is just open to show you what it looks like inside. And we have baffle walls inside to induce better mixing as it goes the way the liquid goes from the bottom and out the top. So in the phase 1, we have COD and nitrate removal occurring. We have about 72% of all the COD being removed, and we have nitrate being removed at 36%. So we saw that there was very low nitrate being removed, and in order to address this issue, we decided to increase the amount of acetate going into the anode chamber. So we saw that once we did that, we saw an increase in the nitrate removal in the cathode chamber, and so we attribute this to the limiting of electrons. So there wasn't enough electrons being passed from the anode to the cathode. So before we had a 4-to-1 carbon-nitrogen ratio, and now we had a 10-to-1 carbon-nitrogen ratio. So after we did those studies. We also did some conductivity studies because we know that real human waste will be high in conductivity. So we saw that by increasing the conductivity of our feed system by 10 times as much as the original, the power increased about 2.5 times as much as the original. And so this was a short-term study, and we also did some long-term studies, but the data was very inconclusive as of now. So in phase 2, we decided to, again, add the nitrification chamber to oxidize the ammonia now to develop the nitrates. And we also fed a new synthetic feces and synthetic urine. And the organics in the synthetic feces were starch, oleic acid, and casein. And the urine was made up of urea and ammonia as the major sources of nitrogen. So this is, again, the laboratory setup now with the anode, the nitrification chamber, and the cathode. And this follows the same schematic as we had before. So again, we have now the data from phase 1 and now the new data from phase 2, and we see that there's quite a bit more of COD and organics going into our system, but we still see a very high removal in the anode. And here we see low amounts of nitrates going into the cathode, and we attribute this to incomplete nitrification in the nitrification chamber. But we still have high removal of the nitrates in that cathode chamber. And here we show the change in the total nitrogen from nitrification effluent to cathode effluent. And this is the soluble nitrogen removal, and there's still some issues going on with the nitrification chamber, and we think there's some hydrolysis happening right now, so we're not seeing all of the ammonia, all the nitrogen that's going into the system coming out. So this is something we still need to study further. So in the phase 1 and phase 2 results, we show that COD and nitrate are both removed, so we do achieve our goal to remove COD and nitrates. But we are seeing very low power production with this large system, and we're thinking that it's probably caused by competing bacteria in the anode. So although the power was very low, we were still able to light an LED light with this large system in the laboratory. So we knew that it is possible to use this as a power source. So now that we did our pilot studies in the laboratory, we took that to Ghana. And first we had to build a composting latrine and then retrofit that latrine with a MFC. So this is how it works. We have a toilet. And solid waste goes in there, and then we have a urinal that diverts male urine into the nitrification chamber. And we have the composting chamber here that filters out the solids, and we have 2 chambers, so when one's in service, the other one's not, so we can close one off and then they can use the other. And here we have the anode. So the solid waste that goes into the toilet goes into the liquid portion of that waste goes into the anode. And here we have the nitrification chamber, and again, the urine that goes into the urinal goes into the nitrification chamber. And both the effluents from the anode and the nitrification chamber both go into the cathode. And the cathode effluent just goes into a filtration bed and then back into the ground. So we used local materials to build this reactor. So we use 60-liter barrels for both the anode and the cathode. We use granular graphite, and we're filled about 2/3 of the way in. And we used dog food as a nutrient for bacteria to grow, and that was only during startup, just to get that bacteria to grow initially. And we also used the pond water that was nearby to inoculate the system with bacteria. And the nitrification chamber was a 55-gallon drum. It was oversized so that we could have a very small liquid layer so that we can reduce the anaerobic layers in there. And we also had, it was built slightly underground so that we could induce mixing by a thermal gradient. And we also added vents so that we can have oxygen going into the system. And this is our completed design. And you can see the top view, the anode cathode nitrification system, and we labeled everything so that students could come by and see how it works. And this was the light source that the MFC powers. So we have some preliminary data from Ghana, and this is the ammonia concentration. So we see initially, while school is in session, we have very high ammonia concentrations. And these values at the bottom are not insignificant, so we're gonna zoom in a little bit and see that nitrification, there is ammonia in the nitrification chamber, but it's very little. And we do see the same ammonia being accumulated in the cathode as well. And here we show the nitrate concentration. And we have, when school is in session, it's very low, but then once it's out of session, we see nitrates being accumulated again in the cathode chamber. It's probably due because no one's using it, so it's accumulating. And here's the power that the MFC in Ghana is producing. And when school's in session, it's higher. It's low, but high. But when school is not in session, it's very low. And this is obviously, it correlates with the usage of the system. If no one's using it, there's not going to be any power. So some of the things we asked of the users was to add wood chips, toilet paper, sawdust to stabilize the compost. And as you can see here, they didn't really put it in the toilet. They just threw it in the latrine, and actually I guess they were using the urinal as a waste container. So I'm assuming that most of the boys who would use this urinal were not being able to use that at this moment. So that could mean that there's an increased amount of urine in the anode and insufficient urine in the nitrification chamber. And so with the Ghana data, we're not able to make any concrete conclusions yet. So we still need further data to be able to see if the system actually works. So for some future work, we want to be able to characterize the oxidation of some of the complex organics going into the anode chamber. We also want to be able to identify the microbial communities in the anode and cathode of the lab-based pilot system, because we know there's some competing bacteria in the anode. We also want to be able to see if we can remove some sort of pathogens from the waste using the MFC latrine. And we also want to be able to assess some of the user interface challenges, because if we can't address those issues, then this system's not going to be viable. And I want to make some acknowledgements. I want to thank the Bill and Melinda Gates Foundation for funding this project. Also the National Science Foundation Graduate Research Fellowship for funding my research. Brad Rogers and Mark Henderson from Global Resolve at Arizona State University, who are our partners in this project, and they had the community relations already established. We also want to thank Charlie and Mary Kay Jackson from Pure Home Water Ghana, who go out and sample for us, and I want to thank the Butler Lab, Jake, Varun, and Chloe at UMass. Thank you.
We have time for some questions.
Oh my God.
Let's start on this side first.
So I see you're using the same tube or maybe pipe to connect anode and cathode.
Yeah.
I feel that's a limiting factor, because you have a very small cross section for iron transport.
Yeah.
So maybe in the future design, you can consider increase that cross area.
Yeah.
To have more iron transport.
Right, yeah, actually I've been thinking about that too. Just, yeah.
I just have a simple question. Since the power production is very low, so how do you power that valve?
So we were able to charge a battery. So we had to we let the electrons go into that battery and charge it for about a day, and then we were able to light that battery.
And how long do you have power that valve?
So it took us 24 hours to charge the battery, and we were able to light it for about 30 minutes.
So I saw you have produced a very little energy. So what percentage of nitrate to remove relate to the MFC?
To which one?
I mean, nitrate can accept the electron from the anode, but what percentage of nitrate removed relate to the MFC?
Well, we're using the nitrate as the electron acceptor in the cathode. And I'm not exactly sure what your question is.
I think there's also organics coming in, so you can just have organics-driven denitrification.
Oh, okay.
Like in urine, you have a lot of uric acid.
I didn't really think about that.
One final question, perhaps? Yes?
I have two questions. The first question is about the nitrification tank. I saw you have two vents there. Do you also spark there, or you just rely on the two vents for the
We only relied on the 2 vents.
and it work?
We're hoping it
Okay.
works.
You have the tank all filled or like half of the tank filled? And for the nitrification?
No, so it's a very large tank so that we have a very small layer of liquid at the bottom. Yeah.
And the second question is about the pH. Do you look into the pH change? First the pH in influent and the pH change in the cathode?
So we have some preliminary data of pH, but it varies a lot. So we're not sure if it's reliable yet to make any sort of conclusions.
Yeah, just comment if you have the after the nitrification tank, you probably can have some like low pH after.
Well, I think we were seeing pHs around 7.
Right. Please join me in thanking our speakers.